Hello everyone. In the previous class, we have seen some of the examples of solutions of Laplace's equation. In that, we have seen one application in finding the capacitance of a parallel plate capacitor. Right? We have found the capacitance as equal to epsilon A by D, which is exactly the same as the equation that we already know. Right? Then today we will see another kind of capacitor, that is a cylindrical capacitor, or you can call it a coaxial cable capacitor. You know how a coaxial cable capacitor is formed. There are actually two uh, conducting cylinders. Okay, two conducting cylinders which are coaxial, which one cylinder has a lesser radius, another cylinder has a larger radius. The center is the same, right? In between those cylinders there is a insulator, a dielectric. So it acts as a capacitor. Okay, so we are going to derive the expression for capacitance of this kind of capacitor, that is coaxial cable capacitor. So consider a coaxial cable, which is as shown in this figure. Coaxial cable means there are two cables, two cylinders which have a common center. Okay, common center or common axis, you can say. In the inner cylinder has a radius A and the outer cylinder has the radius B. Okay, so this is the kind of coaxial cable that we are looking at. So let us assume that the space between the two cylinders is filled with the dielectric. Dielectric means an insulator with permittivity epsilon. Okay, the space between the two cylinders is filled with dielectric or insulator having permittivity epsilon. Okay, then we will also assume that the potential at the outer cylinder, that is at R is equal to B. The radius of the outer cylinder is B. That's why R is equal to B. At that particular, on that particular surface, the potential is zero. That is, it is grounded. V is equal to zero, and the inner cylinder is at a potential V naught. The inner cylinder means R is equal to A. It is at a potential V naught. Okay, so this is our assumption. V is equal to V naught at R is equal to A, and V is equal to zero at R is equal to B, as shown in this figure. Okay, so since the region between the two cylinders, since there is a dielectric in between these two cylinders, it is free of charges. When it is free of charges, it satisfies the Laplace's equation, that is del square V is equal to 0. Okay, so now we will consider cylindrical coordinate system. In cylindrical coordinate system, what is del square V? Del square V is actually 1 by rho, dou rho by dou by dou rho, rho into dou V by dou rho, plus 1 by rho square, dou square V by dou phi square, plus dou square V by dou Z square. So, you know, the radius in case of cylindrical coordinates, that is rho, it in some cases we can also write it as r. It is one and the same. Okay, just to differentiate it between the cylindrical and spherical coordinates, we use r for spherical coordinates and rho for cylindrical coordinates. But when we are sure that it is cylindrical coordinates and the coordinates are r, phi, and z, you know, we can use r instead of rho to make it simple. You know, to write r, it's very easier for us, as we already know that we are familiar with the letter r. Okay, so that's the only reason we take r as radius. Okay, the yeah, in the del square V, expansion of del square V in case of cylindrical coordinates is 1 by r dou by dou r rho into dou v by dou r plus 1 by r square dou square v by dou phi square plus dou square v by dou z square. So what we observe is V is a function of R only, right? V is varying with respect to R only. That is, if R is equal to A, V is equal to V naught. If R is equal to B, V is equal to 0. With phi and Z, it is not varying. That is, the electric field intensity is actually only, it is radiating outward from the inner cylinder to the outer cylinder. So it is in the radial direction. So only dou V by dou R exists. So what I was telling is, our potential, the potential is the function of radius alone. So the components dou v by dou phi and dou v by dou z, they become 0. So what remains is only this particular term, 1 by r dou by dou r into dou v by dou r, right? So that's what we say. Since v is a function of r alone, only dou v by dou r exists. That means dou v by dou phi and dou v by dou z do not exist. Do not exist means these terms become 0. Okay. So what remains is just this term 1 by r dou by dou r into dou v by dou r. This is 0. If this is 0, you know, 1 by r term can be taken this side, so that will become 0. So dou by dou r of r into dou v by dou r is 0. Now what is the next step? We are solving this equation to get the value of v, right? So we need the value of V. That's why we integrate this. Integrating this equation number 2 with respect to Z, with respect to R, what do you get? With respect to R, okay, you are integrating this with respect to R. So what we get, R into dou V by dou R. Integration of this is one differentiation gets cancelled. That is R into dou V by dou R is equal to integration of 0 is 0 plus a constant C1. Okay. So what is dou V by dou R then? R, if you take to the RHS, it comes to the denominator. It is C1 by R. Dou V by dou R is C1 divided by R. So again, integrate both the sides of this equation with respect to R. Okay, sorry, with respect to R. So if you integrate this with respect to R, what do you get? So integration and differentiation gets cancelled. So what remains is V, right? Then what is the integration of C1 is a constant. C1 if you take outside, integration of 1 by R dr. Integration of 1 by R dr is ln R, right? Integration of 1 by R with respect to R is ln R plus a constant C2. Okay, so this is the expression for potential, that is C1 ln R plus C2. Now we have to apply the boundary conditions and obtain the values of C1 and C2. Okay, so in this particular equation 4, we will apply one boundary condition, that is V is equal to V0 at R is equal to A. Okay, in this, if V is equal to V0 at R is equal to A, we will substitute V0 here and A here. What do you get then? You will get V0 is equal to C1 ln A plus C2. Right? V0 is C1 ln A plus C2. Similarly, there is another boundary condition, that is V is equal to 0 at R is equal to B. In place of V, you make it 0. In place of R, you make it B. Then what do you get? 0 is equal to C1 ln B plus C2. From this, what is the value of C2? If you take C1 ln B to the other side of the equation, it will become minus C1 ln B. So C2 is equal to minus C1 ln B. Okay, you take it as another equation, equation number 6. So if you substitute this value of C2 in this particular equation, what do you get? In place of C2, we will write minus C1 ln B. Okay, so V0 will be equal to C1 ln A minus C1 ln B. So C1 is common. So if you take C1 common, what remains is ln A minus ln B, right? What is ln A minus ln B? It is ln of A by B, right? Ln A minus ln B is ln of A divided by B. So from this, you can write what is the value of C1. If I take ln A by B to the other side, it will come to the denominator. So C1 is V0 divided by ln A by B, right? C1 is V0 divided by ln of A by B. This is one constant. Okay, so we will use this. We will use the value of this C1 in previous equation, that is equation number 6. In this equation, then we will get the value of C2. Okay, in place of C1, we will use V0 divided by ln A by B. We will get the value of C2. So this was C1, that is V0 divided by ln A by B into ln B. This is C2. This is another constant. Now, if you substitute both of this, C1 and C2, in equation number 4, we get the expression for V, right? V is equal to C1 ln R minus C2, right? C1 ln R plus C2. This was the expression. V is equal to C1 ln R plus C2. This is C1, that is V0 divided by ln A by B into ln R plus C2. C2 is this minus V0 divided by ln A by B into ln B. Now, what you observe in this is, again, this V0 divided by ln A by B is common in both these terms. If you take this common, then what remains? The factors are ln R minus ln B, right? Again, this ln R minus ln B can be written as ln of R by B, right? That's why we get the expression for V as V0 into ln of R divided by B divided by ln of A divided by B. This is the potential. Okay, this is the potential at any point in between the two cylinders, which is at a distance of R. Okay, where D is the radius of the outer cylinder and A is the radius of the inner cylinder. V0 is the potential on the outer surface of the outer cylinder. Okay, sorry, the surface of the inner cylinder. Surface of the outer cylinder is grounded. That is V is equal to 0. V0 is the potential at R is equal to A, right? So this is the potential, equation for potential V. Now, in our step to find the capacitance, once you find V, we are supposed to get E. E, that is electric field intensity. What is electric field intensity? Electric field intensity is given by E, that is equal to minus del V. Now, again, this del V has rho, phi, and z components, or r, phi, and z components. So since V is a function of R alone, we will take only the R components, that is dou V by dou R AR, right? Del V in terms of only the radial components, if you write, it is dou V by dou R into AR. Plus there will be some phi and Z components, which we eliminate because they are 0. We are taking only the R component, that is dou V by dou R into AR. So V, you already know, we have found it in the previous case, in the previous equation. Just substitute that thing. That is V naught ln R by B divided by ln A by B. If you differentiate this with respect to R, okay, what do you get? So first take the unrelated terms outside, that is V naught divided by ln A by B, then dou by dou R of ln R by B with respect to, dou by dou R of ln R by B, direction is AR. So what is differentiation of ln R by B? That is 1 by R, right? Differentiation of ln R by B is 1 by R. So that's why E is equal to minus V naught into R ln A by B AR. This is the expression for electric field intensity. Okay, that is minus V naught divided by R ln A by B AR. Once you get electric field intensity, we are supposed to get electric flux density. What is electric flux density? D, that is equal to epsilon into E. So whatever you have this expression, multiply this with epsilon, you get electric flux density. That is epsilon into this. So I can write this as minus epsilon V naught divided by R ln A by B AR. Once you get electric flux density, you take the normal component of this. What is the normal component of this? Normal component is nothing but the magnitude, right? The magnitude of this, magnitude is epsilon V naught divided by R ln A by B, right? Epsilon V naught divided by R ln A by B, right? So this is the normal component. Then we equate this normal component with the surface charge density rho s. That is surface charge density rho s is equal to dn. So rho s is epsilon V naught divided by R ln A by B, right? So this is the surface charge density, epsilon V naught divided by R ln A by B. Then multiply this with the area of the surface. You get the charge. If this is rho s, charge is given by Q, that is rho s into A, right? Rho s is this particular thing, that is epsilon V naught divided by R ln A by B. Substitute that here, epsilon V naught divided by R ln A by B multiplied by area A. Now what area is this A? Area A is the surface area of a cylinder. What is the surface area of a cylinder? If the radius is R and the length of the cylinder is L, the surface area of the cylinder is 2 pi R into L, right? So 2 pi R into L. So substitute it here. It is 2 pi R into L, right? So what happens? This R is common in numerator and denominator. It gets cancelled. What remains is 2 pi epsilon V naught into L divided by ln of A by B. Okay, 2 pi epsilon V naught L divided by ln of A by B. This is the charge. Okay, this is the charge. Once you get the charge, you can find the capacitance by the equation charge divided by potential. That is Q divided by V. C is equal to Q divided by V. This is Q. And what is V? V is the potential difference. Potential difference between the two coaxial cables. The inner cable is at a potential V naught. Outer one is at a potential 0. So potential difference is V naught minus 0. Okay, V naught minus 0, that is V naught. So V naught and V naught, if it gets cancelled, so this is the capacitance of a coaxial cable capacitor. That is 2 pi epsilon L divided by ln of A by B, where A is the radius of the inner cylinder, B is the radius of outer cylinder. So it is B is greater than A. Okay, B is greater than A. Epsilon is the permittivity of the dielectric medium which is present in between the two cylinders, and L is the length of the cylinder, length of the capacitor or length of the cylinder. Okay, sometimes they might ask you to find the capacitance per unit length. What is the capacitance per unit length? Divide this by L to get the capacitance per unit length. So the unit for that is farads per meter per length. Okay, capacitance per length is farads per meter. If you divide this by L, what happens? You will get 2 pi epsilon divided by ln of A by B. Okay, L gets eliminated because it is per length. Okay, so it is 2 pi epsilon divided by ln of A by B. Unit is farads per meter. Okay, so this is what, that is the capacitance of a cylindrical capacitor or coaxial cable capacitor. Okay, similar to this, we have one more capacitor, that is spherical capacitor, which is formed by two concentric spheres, two concentric conducting spheres, in between, which is filled with dielectric. In between the two spheres, we have a dielectric of certain permittivity. Okay, so that's the next one. It is capacitance of a spherical capacitor using Laplace's equation. So consider two concentric spheres of radii A and B. That means the inner radius is A and the outer radius is B. So B is greater than A, right? B is greater than A. So let us assume that the space between the two spheres is filled with dielectric with permittivity epsilon. Okay, this is a sphere. Okay, you have to imagine a sphere. That means in 3D, that is something like a ball. There are two spheres, one within another. Inner one has radius A, R is equal to A. Outer one has radius B. Let us assume that the outer sphere is grounded. So V is equal to 0 at R is equal to B. And the inner cylinder is at a potential V is equal to V0. Okay, the inner one is at a potential V is equal to V0. V is equal to V0 at R is equal to A, and V is equal to 0 at R is equal to B. Okay, since the region between the two spheres is free of charges, because it is a dielectric, right? There are no charges. It satisfies Laplace's equation. That is del square V is equal to 0. Now you consider the spherical coordinates. What is the del square V in spherical coordinates? It is 1 by r square dou by dou r of r square into dou v by dou r plus 1 by r square sine theta dou by dou theta sine theta dou by dou theta plus 1 by r square sine square theta dou square v by dou phi square. So actually, you know, it is also enough just to write the r component here. Even if you do not write this, it is okay in this case, because these terms are essentially 0 in this case. Okay, because here again, V is a function of r alone. We write here like V is V0 at R is equal to A and V is 0 at R is equal to B. That is, V is varying with respect to R. It is moving, the electric field intensity is moving radially outside from the inner sphere to the outward sphere, right? There is no theta or phi components of electric field intensity. So that's why there is no theta and phi components for the potential also. So dou v by dou theta and dou v by dou phi are 0. That's why it is also enough just to write 1 by r square dou by dou r square into dou v by dou r. Okay. Otherwise, you can write entire thing and then say V is a function of r alone. So only dou v by dou r exists. That is dou v by dou phi and dou v by dou z are 0. So what remains is only this particular term, that is 1 by r square dou by dou r into r square dou v by dou r. So this term will be 0. Now 1 by r square I can eliminate from here. So what you get is dou by dou r square dou by dou r is 0. Now we are solving this equation to find V, right? To find V, you have to integrate this. If you integrate both sides of this particular equation with respect to r, what do you get? So integration and differentiation, one differentiation gets cancelled. So r square into dou v by dou r will be equal to 0 plus C1. Right? R square into dou v by dou r will be equal to C1. So if I take r square to the other side of the equation, it comes to the denominator, that it will become C1 divided by r square. This is dou v by dou r. Now to find V, again I have to integrate this with respect to r, right? I have to integrate this with respect to r. If I integrate with respect to r, differentiation and integration, they get cancelled out. What remains is only V. So it is integration of C1 divided by r square with respect to r. Right? So what is C1? You can keep it outside. So integration of 1 by r square is minus 1 by r. Right? Integration of 1 by r square is minus 1 by r. So this is V, which is equal to C1 into minus 1 by r plus C2. Another constant, C2. So C1 into minus 1 by r, I can write it as minus C1 divided by r. So this is the expression for V. Right? Now you have to apply boundary conditions and get the values of C1 and C2. You have to apply the boundary conditions and get the values of C1 and C2. We have two boundary conditions. V is equal to 0 at R is equal to B. V is equal to V0 at R is equal to A. We'll apply the first one. V is equal to V0 at R is equal to A. Right? So here we will apply V is equal to V0, R is equal to A. So what do you get? V0 is equal to minus C1 by A plus C2. Right? So you take this as equation number 5. You apply another boundary condition, v is equal to 0 at r is equal to b. So that equation will become 0 will be equal to minus c1 by b plus c2. From this, what is the value of c2? If I take this minus c1 by b to the other side, it will become c1 by b. So c2 will be equal to c1 by b, right? So substitute this here. Substitute this in equation number 5. What do you get? C2 will be equal to C1 by B. So in place of C2, I can write C1 by B. So V0 is minus C1 by A plus C1 by B. In both of these, C1 is common. If I take C1 common, the factors are minus 1 by A plus 1 by B. From this, what is C1? If I want to get the expression for C1, this minus 1 by A plus 1 by B, it will go to the denominator, right? So C1 is V0 divided by minus 1 by A plus 1 by B. So this is one constant C1, that is V0 divided by minus 1 by A plus 1 by B. So substitute this in equation number 6, you get the constant C2. Okay, so if you substitute this in equation number 6, you get the constant C2. C2 will be equal to, it is C1 by B, right? C1 is this V0 divided by minus 1 by A plus 1 by B divided by B. So you get this. B is in the denominator. This is the constant C2. Substitute both these constants in equation number 4. What is equation number 4? Minus C1 divided by R plus C2. That is V1, right? V is minus C1 divided by R plus C2. So C1 is V0 divided by R into minus 1 by A plus 1 by B. So minus C1 by R plus C2 is V0 divided by B into minus 1 by A plus 1 by B. Again, what is common in this case, or you can take, since there is minus here, if I multiply minus term inside this, I can write it like this. V0 divided by R into 1 by A minus 1 by B. If I multiply minus into minus into plus is minus. So this will become, instead of minus 1 by A plus 1 by B, I can write this as 1 by A minus 1 by B, right? Similarly here, I can take minus here. So if I take minus, plus into this will become minus. If I take minus sign, so this sign will change. So minus will become plus and plus will become minus. So this is one and the same, right? Instead of writing plus and taking minus and plus here, if I write minus here, so I can replace it with the same thing that I have in the other term in the RHS. That is 1 by A minus 1 by B. Now, what is common among this? V0 divided by 1 by A minus 1 by B is common. And what is the factor? 1 by R minus 1 by B. 1 by R minus 1 by B is the factors, right? So this is the expression for the potential at any point in between the two concentric spheres. That is V0 divided by 1 by A minus 1 by B multiplied by 1 by R minus 1 by B. Now, once you get this V, you can find E by using E is equal to minus del V, right? E is equal to minus del V. So again, del V, since V is a function of R, we will take only the R components. R component in del V is only dou V by dou R into AR. The theta and phi components we can just eliminate because those are 0. So substitute this V, that is this particular thing in this equation. You'll get this. So differentiate this with respect to R. You can keep this term outside, minus V0 divided by 1 by A minus 1 by B outside. Then differentiate this with respect to R. Okay, what is differentiation of 1 by R minus 1 by B? Differentiation of 1 by E is 0. What is differentiation of 1 by R with respect to R? It is minus 1 by R, right? Differentiation of 1 by R is minus 1 by R square. So you get this. So what remains is V0 minus into minus, you can take it as plus. So what you get is V0 divided by R square to 1 by A minus 1 by B AR. This is the expression for electric field intensity. From this electric field intensity, we can get electric flux density by using D. That is, D is equal to epsilon into E, right? D is equal to epsilon into E, multiply epsilon. That's all. Epsilon with this E, you get D. Now, from this electric flux density, what is the normal component? It is the magnitude. Magnitude is epsilon V0 divided by R square into 1 by A minus 1 by B. This is the normal component Dn. Then equate this normal component to the surface charge density rho s. So rho s is the same, that is epsilon into V naught divided by R square into 1 by A minus 2 by B. Now, what is your charge? Charge is rho s into A, right? Rho s into A. So rho s is this particular term multiplied by area A. What is area here? Area is the surface area of a sphere. What is surface area of a sphere? Okay, the surface area of a sphere is 4 pi r square, right? It is 4 pi r square. So just substitute it here. R square is common, it gets cancelled. What remains is 4 pi epsilon V naught divided by 1 by A minus 1 by B. This is the charge Q. Now, what is capacitance? Capacitance is Q divided by V, right? Q divided by V, that is charge divided by potential difference. V is potential difference between the two spheres. The inner sphere is at a potential V naught, outer one is at a potential 0. So it is V naught minus 0. So what you get is 4 pi epsilon V naught divided by 1 by A minus 1 by B divided by V naught. The V naught you can cancel it. So what remains is, see, is 4 pi epsilon divided by 1 by A minus 1 by B, right? So this is the capacitance of a spherical capacitor, okay, with the inner sphere at radius A and outer sphere at radius B. And the space between the two spheres is filled with the dielectric epsilon. Okay, so this is how you can use your Laplace's equation to get the values of capacitances of different types of capacitors. We have seen it for parallel plate capacitor, cylindrical capacitor, and spherical capacitor. Okay, so in the next class, we will try to solve some problems on this. Okay, or we will move on to the next topic, that is steady magnetic field, right? So I will end the session for today. We'll meet in the next class.